Okay, today we start studying tests of significance. Okay, so this is a very typical statistical problem. Okay, let's start. So in probability theory, we assume that we know all the information to calculate the probability. For example, given that a coin is unbiased, then we want to know, for example, what is the probability. Probability that probability that we have let's say probability of obtaining 17 heads out of 40 flips. Okay, so in this problem we are assuming that the coin is unbiased. Okay, given this information, we want to calculate the probability of having 17 heads out of 40 flips. So that is to calculate this probability that we obtain 70 heads. And out of 40, given that coin is unbiased, okay? So this is a typical problem in probability theory. So this is probability theory. Okay. On the other hand, in statistics, we ask a different question. So we observed, for example, 17 heads out of 40 flips. So this is the given information. Then we ask a question: is the coin unbiased? So this is the question. So it looks like we want to calculate this probability that the coin is unbiased. Given the experimental results, 17 heads out of 40. Okay, it looks like we want to calculate this. So if this somehow if we can calculate this probability and this probability is high, close to 1, then we are pretty sure that the coin is more or less unbiased. On the other hand, if this probability is very small, like close to 0, then we can be pretty sure that the coin is somehow unbiased, somehow biased, right? And indeed, this is the approach we use in Bayesian statistics. But that is not quite a standard approach. What we do in so-called frequentist approach is to actually calculate this probability by pretending that the coin is unbiased. We don't know for sure if the coin is really biased or unbiased, but we just assume it is unbiased. it is unbiased, then based on that, we calculate this probability. Okay? And if this probability is very small, then that means it's unlikely to happen. So this result is unlikely to happen if the coin is unbiased. Then that means maybe our assumption was wrong. So we reject the hypothesis that the coin is unbiased. So the coin is therefore somehow biased. Okay, so this approach is called frequentist approach. So it's often contrasted with Bayesian. Okay, but you should notice the subtle difference between probability theory and frequentist statistics. Okay, in probability theory, we do know that a coin is unbiased. Okay, that's the given information. On the other hand, in frequentist statistics, we don't know if the coin is unbiased or not, but we just assume, we hypothesize that the coin is unbiased, and based on that, we calculate the probability of observing a particular result. Then if the probability is very small, we reject the hypothesis because it is unlikely to happen based on the hypothesis. Okay, and this hypothesis is called the null hypothesis. Null hypothesis in this case. Okay, but you should be careful that if this probability is high, it doesn't mean our assumption or hypothesis is correct. It just means we could not reject our hypothesis. Okay, so this is a kind of twisted argument. So hypothesis testing or test of significance so we assume some hypothesis. So for example, a coin is unbiased. Okay, let's call it, it's a null hypothesis. We often write as H0, H0. Then we calculate the probability of observation. Maybe I should write data given hypothesis. Okay, if this is small, then we reject hypothesis. If this is large means greater than some small value, then not reject. So not reject is not equal to accepting. Okay, why is that? Because there can be another hypothesis that can give even larger probability, right? So in that case, that another alternative hypothesis is more likely to be correct than our current hypothesis. So therefore, not rejecting does not mean accepting. Okay? Okay. Now let us look at an example of significance tests for the binomial distribution. We are interested in whether a coin is biased or unbiased. Okay, so our hypothesis here is that the coin is not biased. So coin is unbiased. So we do experiments. And 100 flips of coins. Okay, so suppose we had 50 heads and 50 tails. So in this case, we can model this experiment as a binomial distribution. So the probability of having h equal to 50 is given by the binomial distribution, binomial probability. So 50. Unbiased means probability of head is 0.5 or 1/2. Okay, so that's 1/2 to the power of 50 and 1/2 to the power of 50. Okay, so this 1/2 is 1 minus 1/2. Okay, so well, you can calculate this probability. It's not easy, but if you can approximate by the normal distribution, then the expectation value of this number of heads is this. Okay, wait a minute. First of all, this h follows the binomial distribution with these parameters. Okay, 100 flips with unbiased coin. So its expectation value is, if you remember, this is n and this is p, so it's 100 times 1/2, that's 50. And variance, if you remember, it's np times 1 minus p, which should be 100 times 1/2 times 1/2, so it's 25. Okay, so you can approximate this binomial distribution by the normal distribution. Five exponential h minus 50 squared and 2 times 25. Okay, but anyway, this probability is not so big. I think it's less than 1%. No, less than 10%. Even if the coin is unbiased and exactly having 50 heads, its probability is not so big. It is very likely that it is almost equally likely that we get like 48 heads and 52 tails and so on. Okay, and we can calculate the probabilities of this observation in a similar manner. So probably even if the coin is unbiased, this is just fine. Okay, but what if we have this observation, only 5 heads and 95 tails? But this looks very unlikely, right? So we can have any number of heads out of 100 flips, like from 0 to hundreds. But some values, extreme values of number of heads is highly unlikely. So, for example, let's see. So if we normalize, standardize this random variable h, we have this z and h minus 50 and divided by 5, which is the standard deviation. Okay, this 5 is of course the square root of the variance, which is the standard deviation. So what we want to do is to calculate the probability that this okay, takes some extreme values. Okay, so k is like 2 or 3. So for some k, this becomes less than like 5%. And if we get any value of z that satisfies this inequality, that gives us the probability less than 5%, then we reject our hypothesis. Okay, so this probability is actually a conditional probability. Okay, that the coin is unbiased. So that means p is equal to 0.5. Okay, if this probability is very small, and very small means usually we use 0.05 or 0.01, something like that. But this is quite arbitrary. As long as it's reasonably small, it's okay. Okay, so in this case, suppose, let's say we have, if we want to find the maximum value of k, a minimum value of k, which satisfies this inequality, less than 5%, k would be about 1.95. Okay, so this is like this. If you have a standard normal distribution, okay, so this is z, and this is 0, so this is about 1.96, and this is about negative 1.96. So these probabilities in total, this area, okay, this area plus this area will be less than 5%, 0.05. Okay. So since in this case, assuming this 5, so if this is greater than 1.6, this means so if you multiply both sides by 5, so h minus 50, 1.96 times 5, and if you remember the definition of the absolute value, this means h minus 50 is greater than this, or minus h minus 50, so or is greater than this. Or in other words, so this is, so if you multiply both sides by -1, it means this. Okay. So after all, we have either h greater than, number of heads greater than 50 plus 1.96 times 5, or h, number of heads less than 50 minus 1.95 times 5. So that is, let's see, that's 59.8, and this is 40.2. So if you get number of heads either greater than 60 or less than 40, then we would say with 55% significant level, we reject our hypothesis that the coin is unbiased. Okay. So of course, if we employ 1% significance level, then this number will change. Okay. Instead of 1.96, we use some other value. And what value should we use? You should look up the table of the standard normal distribution, which gives you the probability of less than 1%. Okay. In the standard, if you look up the table, you should look for the number that gives you. So what we want is this number here. So let's say this is Z1. So this is negative Z1, such that the sum of these shaded regions is 0.01. Okay, this plus this is, so that means this is half of this. Okay, so that is 0.005 here, and this one is 0.005 here. But usually the table gives you the cumulative distribution function, so it will give you, maybe I should use this one, this area. Okay. So you look for the number that gives you 0.005 here, and that's the number you want to find for this k. Instead of 1.96, you will have something else. So if we go back to the previous example, if we have 50 heads, then we do not reject the hypothesis. And if we have 48 heads, we do not reject the hypothesis. But if we have only 5 heads, and of course 95 tails, then we do reject the hypothesis. So if we ever get this result out of 100 flips, then we reject the hypothesis that the coin is unbiased. So we conclude that the coin is biased. Now let us consider another example. So that is testing the effectiveness of a drug. Suppose there is a pharmaceutical company called UBD Pharma, and they developed a new drug called X. Okay, and they tested this drug to 125 patients, out of which 81 were cured and 44 were not cured. Okay, we want to know whether this drug is really effective or not. And to do so, we compare this result with a control experiment. And control experiment is done by using a placebo. Placebo is a fake drug, so to speak. So it doesn't have any effects on the patients. So it just mimics a drug. It looks like a drug, but it doesn't do anything. Okay? So if a patient is cured just by having a placebo instead of the real drug, then if the result doesn't differ much, then the drug is not effective, or is just effective as placebo. No, it means it does nothing. Okay, so But what we want to do is to show that this drug is really effective. Okay? So how can we do this? By using a significance test. So that is done by setting a hypothesis that drug X and placebo are no different. So drug X and placebo are equally effective or equally ineffective. Equally ineffective. So they're not effective. And if we can reject this hypothesis in favor of drug X, then indirectly we prove, we show that this drug is effective. Okay? So, in order to do that, let's say P is the probability that a patient is cured, either by drug X or placebo. Since our hypothesis is that they have no difference, so the probability should be the same. Okay? That a patient is cured. Okay, and let's say Q is 1 minus P. Okay, and let's say this 125 as N1 and this is N2. Okay, so let's say X, so this is experiment 1, experiment 2. Okay, so X1 is the number of patients cured in experiment 1. Okay, and X2 is the number of patients cured in experiment 2. Okay, so since a patient is either cured or not, and we do this experiment repeatedly for this population, X1 follows a binomial distribution with parameters N1 and P. Okay, this N1 is 125. Okay, and X2 follows the binomial distribution with parameters N2 and P. Okay, so from this we can calculate the probability that patient is cured. Okay, so probability that a patient is cured in experiment 1. Okay, and probability 2, x2 over n2, so same in experiment 2. Okay, what we want to see is that whether P1 minus P2 is significantly different from 0. Okay, if this is a large positive number, then we may reject the hypothesis that they are actually equal. Okay, our null hypothesis is that this is P1 is equal to P2, right? But if that is so, then P1 minus P2 should be 0. But if the real value is different, significantly different from 0, then we reject the hypothesis that they are equal, so that the drug X is indeed effective. Okay, In order to do so, we want to find the distribution to which P1 minus P2 follows. Okay, so what kind of distribution is that? Of course, it will be a normal distribution, but let's see how we can get this. So, since x1 follows this binomial distribution, we have the variance of x1 is n1 p q. Okay, and variance of x2 is n2 times pq. These are the results of binomial distribution. Okay, so the variance of p1 is the variance of x1 over n1. Okay, in the case of variance, a constant comes out, but it's squared. Okay, so x1, but the variance of x1 is this, so we substitute it. So n1 pq n1 squared, so 1n here and here cancelled, so this is pq over n1. And similarly, we have variance of p2 as pq over n2. Okay, then based on that, what's the variance of p1 minus p2? You know, we are assuming that this p1 and p2, they are independent. Okay, p1 and p2 are independent. Okay, in that case, okay, let's write like this, minus 1 times p2. Okay, so if they are independent, we can split the summation. Okay, since they are independent, we can split the summation. Okay, so independent. Now, it's a variance, so this constant can come out, but it should be squared. So negative 1 squared, which is just 1, so we can get rid of it. So it's just a summation of this and this, so they are these. So we have pq and 1 over n1 and 1 over n2. So pq times 1 over n1 plus 1 over n2. Okay? So, after all, we assume that this p1 minus p2 follows the normal distribution with mean 0 and variance pq times 1 over n plus 1 over n2. Okay, at this point we don't know the value of this p, so we approximate this by combining the two experiments. Okay, so two experiments, so these numbers divided by these numbers. Okay, so we approximate p by, let's see, 81 plus 145 divided by 125 plus 241, which is, let's see, approximately 0.61, I would say 8. Okay. So if you use this value, then of course Q is 1 minus P. So the variance would be, so N1 is 125, N2 is 241. So the variance should be about like 0.00287 or so. Okay, so if you take the square root, this would be approximately 0.0536 or so. Okay, and from the table, P1 can be estimated as 81 over 25, and P2 can be estimated as 145 over 241. So if this difference follows the normal distribution, then what's the probability that Z, so P1 minus P2 over this variance, let's say this is, suppose this is sigma. So if this is greater than this value, so if you plug in all these values, this should be something like, let's see, 0.865 or so. So if the probability that this Z value is greater than this value is less than, okay, let's write it down. If the probability of this is less than 0.05 or so, then we may conclude that the drug, conclude that our hypothesis was wrong. Okay, so reject it. So if you look at the normal distribution, so we look at this area. So this is this number. Okay. If this part area is less than 0.5, then we reject the hypothesis in favor of drug X. So that will prove that the drug is effective. So is this really so? Less than 0.05? Let's look at the table of the normal distribution. So let's see. It's what was the value? 865. Okay. So 865. So let's see. 8. 6. Let's see. 86. Around this area. So, okay, so somewhere around here. So either way, the probability will be around 0.85 or 7 or so. So unfortunately, this probability is not small enough. This probability is about 0.8 something. So it's pretty high. So we cannot reject our hypothesis that the drug and placebo are equally effective. So yeah, that's it. That was unfortunate, but anyway, that's the result.